In this lesson, we're going to learn about a couple of more identities. In this case, we're going to learn about the double and the half angle identities. Now, the double and half angle identities are identities where you're taking the sine or the cosine or the tangent of twice an angle or half an angle, hence the name double or half angle identities. So something like this. The sine of 2x. I'm taking the sine of 2 times something. This would be my double angle identity. Or I'm taking the cosine of 2 times something. So that would be my double angle identity for cosine or for tangent. Now the answers for these are as follows. The sine of 2x is 2 sine x. The sine of cosine 2x is cosine squared x minus sine squared x. Or we could do 2 cosine squared minus 1, or 1 minus 2 sine squared x. Tangent 2x is 2 tan x over 1 minus tan squared x. So these are our identities. Why they are what they are, we'll see in a second, but there's something that's important to know, is that if you look at this, remember, cosine of theta is not cosine times theta, it's cosine of theta. So the cosine of 2x or the sine of 2x, etc., is not sine times 2x or cosine times 2x, it's cosine of 2x. So I can't just take this 2 and pull it outside of this thing. That doesn't work. These two things are not equal to one another. I can't say that the cosine of 2x is equal to 2 times the cosine of x, because they're not. I can't just pull the 2 out in front. The cosine of 2x is equal to cosine squared x minus sine squared x. It's a common mistake a lot of people make, and it's something that you cannot do. Okay? Now that being said, why are the answers what we're seeing up here? Well, they have to do with the sum identities. So we'll show why these identities are what they are because of the sum identities. So what do we know? We know that the sine of alpha plus beta is equal to the sine of alpha cosine of beta plus the sine of beta cosine of alpha. So if that's the case here, if I think of the sine of 2x to be sine of x plus x plus x being 2x, this is a sum. And if this is a sum, think about this one as my alpha and this one as my beta. So I'm going to get the sine of x times the cosine of x plus the cosine of x times the sine of x. But these are the same thing. There's two of them, so we get 2 sine x cosine x. If I did cosine of 2x, that's cosine of x plus x, which is going to be, for that sum identity, it's going to be the cosine of x times the cosine of x minus the sine of x times the sine of x, which would be cosine squared x minus sine squared x. Hence this. Now we have two other versions of this identity. That could be useful depending on what you're doing. Sometimes you just want to write your answer in terms of sine. Sometimes you just want to write your answer in terms of cosine. I'd say you're going to use this most often, but then that could get you these other two. Now where did these other two come from? Well, they come from the fact that sine squared and cosine squared can be written using the Pythagorean identity. Cosine squared is 1 minus sine squared x. And if I have another minus sine squared x, then I get 1 minus 2 sine squared x, giving me this. I could also, instead of taking cosine squared and writing it this way, I could have took sine squared and wrote it as 1 minus cosine squared, and got the same thing and came up with this identity. So there's lots of different ways to write the double angle identity for cosine. And then the tan comes again from the sum identity for tan, translating into x plus x, alpha and beta being x and x, you would get this. Knowing where the identities come from is a good thing to know. Most of the times it's not as important as knowing how to work with them. However, this one is pretty important. This technique of how we break apart this into a sum and then use the sum identity to come up with the answer can be very useful. Later on, we're going to talk about finding the sine of 3x or the cosine of 4x, etc. Well, this would be like a triple angle identity. This would be a quadruple angle identity that we're looking for. Well, if I break it apart the same way, think of this as sine of 2x plus x, or this one being the cosine of 2x plus 2x. If I start them off that way and start thinking about them as a sum identity, I can then eventually get it into, sine x and cosine x. I can break it down. Anything with a 2 inside of it, or a 3 or 4 inside of it, I can eventually whittle down to just all x's by using sort of this method. So this sort of why it is what it is explanation, the proof of these things, is fairly important for this particular example. Now, really, you want to learn how to use the identities. So, one thing we can use the identities for is to evaluate trig functions. However, the double angle identity, it's not really useful in terms of evaluating trig functions, because what we did last time is we said, okay, think of an angle that's not a special angle, 75 degrees. Are there any two angles that we could add or subtract together to give you 75 degrees? In that case, 45 plus 30. So here's two special angles I could add together to give me 75. So I can use a sum identity of special angles to get an angle I'm not used to working with. However, when it comes to these double angle identities, I say, is there any angle that I know how to work with that if I double it creates another angle I don't know how to work with? Well, the answer to that is no. Like twice 30 is 60. Well, I already know how to deal with 60. Twice 60 is 120. I already know how to work with 120. Twice 45 is 90. I already know how to work with 90. So I don't get another angle that I don't know how to work with like I did here. I could add two special angles together and get an angle I'm not used to working with, and then somehow use this to help me find, say, the cosine of this. But for double angles, it's not the case. I can't use this to help me find this. Well, I could, but it's not really pointless. It's not really worthwhile. So, I mean, we'll just do a couple examples so you see it, but this is something you really wouldn't do in the long run. Alright, so let's erase. So if I wanted to say the sine of 60, if I wanted to use a double angle identity, I would say, what special angle, when I multiply it by 2, gives me 60? And that's easy. 2 times 30. So if I use the fact that sine of 2x equals 2 sine x cosine x, then in this case my x is my 30. So sine of 60 is the same thing as sine of 2 times 30. And sine of 2 times 30 is going to be equal to 2 times the sine of 30 times the cosine of 30 degrees. Well, 2 times the sine of 30 degrees, 30 degrees being square 1/2, and cosine of 30 degrees being square root of 3 over 2. I cancel these, I get square root of 3 over 2. But guess what? I can find the sine of 60 degrees much easier than doing this. I should just know that when I look at 60 degrees on the unit circle, the y-coordinate is square root of 3 over 2, and so the sine of 60 is square root of 3 over 2. This is the long way of doing it, but you can, in theory, use the double angle identities to do any of these. What you're more likely to do is probably use the double angle identity to do something like this. Well, you want to verify that the sine of 4x over 4 equals cosine cubed x sine x minus sine cubed x cosine x. So what I'm going to do is this. Use the same technique we used before. I'm going to take this 4 and move it to the other side. So I'm going to have sine 4x equals 4 times cosine cubed x sine x minus sine cubed x cosine x. So I'm going to write the sine of 4x as the sine of 2x times 2. So think of this like a double angle identity. This is 2 times this. So if I use a double angle identity, then this should be equal to 2 times the sine of 2x cosine 2x. This thing being what was my x in the identity. Well, each one of these is its own double angle identity. So I get 2 times 2 sine x cosine x. That's the double angle identity for sine. Times the double angle identity for cosine is cosine squared x minus sine squared x. Well, if I distribute this in here and multiply the 2's, I'm going to get 4 times sine x cosine cubed x minus sine cubed x cosine x, which was exactly what I was trying to turn this into. So that verifies that it's true, that one side in fact equals the other side. So this is more likely what you're probably going to be using the double angle identities for. Now that we talked about the double angle identities, next up is the half angle identities. So the half angle identities, instead of taking the sine of 2 times something, we're taking the sine of half of something, or cosine of half, or tangent of half. So this is what the identities look like. This would be the half angle identity for sine. This would be the half angle identity for cosine. And then there's 3 different versions of the half angle identity for tangent. I'd say most of the time, this one is probably most convenient in that, 1, it doesn't have roots like these other ones do, which are not always nice to work with. 2, you have a single term in the denominator, just sine, which allows you to do a little trick that we've done many times, is split up the numerator 1 over sine x minus cosine x over sine x. And 3, it's written in terms of sine and cosine, which tends to make things easier anyway. So why are these identities what they are? Well, it has to do with the double angle identity and sort of looking at the double angle identity and almost working backwards. So if I look at this equation here and I solve for this cosine x, I'm going to add 1 to bring it to the other side and then divide by 2. So I get cosine squared x equals cosine 2x plus 1 over 2. I can also write that as 1 plus cosine 2x over 2. This identity, actually, this thing right here that you're looking at, actually has a name to it. Cosine squared x equals 1 plus cosine 2x over 2. The name of that is called the power reducing identity. It's not really that important for you right now. It is just another identity that has a specific name that does come up at a later date. So while we're here, I might as well just point it out to you. But anyway, if I take rid of the square, I have to take the square root, so I get the cosine of x equals the square root of 1 plus cosine 2x over 2. But whenever you do the square root, you got to do the plus and minus the square root. And then here's where the trick comes in. I'm going to take this x and I'm going to replace it with an x over 2. Well, this x over here is the same x, so that x has to be replaced with an x over 2. However, this one was multiplied by 2, so the 2 and the half cancel. And what I end up with is the half angle identity, that cosine of x over 2 equals plus or minus the square root of 1 plus cosine x over 2. So that's where the identity comes from. This one is less important to know where it comes from, but it doesn't hurt. Now, unlike the double angle identity, the half angle identity can help us find the cosine, the sine, the tangent of angles we haven't found before. Because half of our special angles do create new angles. 45 divided by 2 is 22.5. 30 divided by 2 is 15. These are not special angles, but the half of a special angle gives us these things, so we can use the half angle identity to help us find the sine, the cosine, and tangent of these kinds of angles. So if I look at the cosine of negative 22.5 degrees, that's the same thing as saying let's take the cosine of negative 45 degrees divided by 2. Well, if you think about the half angle identity for cosine, we just said cosine of x over 2 is equal to plus or minus the square root of 1 plus cosine x over 2. So, x in this case is negative 45. So this should be equal to plus or minus. Now I'm not going to use the plus and minus in this one because this is negative 22.5, which is ultimately what we're trying to find the cosine of. Negative 22.5 is in the fourth quadrant. The fourth quadrant cosines should be positive. So I'm just going to use the positive square root of 1 plus cosine of negative 45 degrees over 2. Because that's my x. As far as this plus and minus goes, the only time you're going to use both the plus and the minus is if you're taking the cosine of an angle that you have no idea where that angle falls. So say it's a random angle. Say I'm just doing the cosine of theta over 2 and I'm using this identity. Well, theta is just some random angle. It could be in any quadrant. Theta over 2 could be in any quadrant. So I don't know whether I should use a plus or minus. But this one, I know negative 22.5 quadrant 4, cosine of quadrant 4, positive. Alright, let's finish this off. So I get the square root of 1 plus the cosine of negative 45 is square root of 2 over 2. All over 2. Now it's just a matter of simplifying this thing. So if I take this numerator and I use common denominator and write this as a single fraction, I get the square root of 2 plus root 2 over 2. That's just this numerator part here. Then that whole thing is still divided by 2. That's this 2. Which gives me the square root of 2 plus root 2 over 4. These two have to be multiplied together. Then that gives me the square root of 2 plus root 2 all over 2. Because I could take the square root of the numerator and the square root of the denominator separately, and the denominator would give me 2. So that is my final answer. That's what the cosine of negative 22.5 degrees is. So we don't need a calculator to calculate the exact value of that angle. What about this one? Sine of pi eighths. Well, if I think about the sine of pi eighths is pi fourths divided by 2. Because if I divide pi fourths by 2, I multiply the denominators, and that gives me pi eighths. So, if I use the half angle identity for sine, which is x over 2, is the square root, plus or minus, the square root of 1 minus cosine x over 2. Then this becomes really x being my pi fourths, then this becomes the plus or minus, but pi eighths is in quadrant 1. Quadrant 1, cosine and sine are both positive, so I do positive square root of 1 minus cosine pi fourths over 2, which is the square root of 1 minus square root of 2 over 2, all over 2. This is the exact same thing as the last one, except for we have a minus instead of a plus. So my answer is going to be the square root of 2 minus root 2 all over 2, because it simplifies the exact same way as the last one. Other things you can do with the half angle identity are questions like this. Find the cosine of alpha over 2 given that the sine of alpha is 1/3 and that alpha is between pi halves and pi. Well, if alpha is between pi halves and pi, then alpha is in quadrant 2. Because quadrant 2 is between pi halves and pi, 90 and 180. The cosine of alpha over 2 is equal to plus or minus the square root of 1 plus cosine of alpha all over 2. Well, we know what the sine of alpha is. In order to do this, we need to know what the cosine of alpha is. So how are we going to get that? First thing we're going to need to do is use sine squared alpha plus cosine squared alpha equals 1. Sine being 1/3, so 1/3 squared plus cosine squared equals 1. So cosine of alpha equals the square root of 1 minus a ninth, plus or minus. Alpha being in quadrant 2, cosine is going to be negative, so we want the negative here. So we get negative square root of 8/9, or negative 2 root 2 over 3. That then has to go in here, and I would get plus or minus, but actually I could do plus, because if I have an angle that's in quadrant 2, here, somewhere in here, and I take half of it, well, the biggest it could be would be pi, and half of pi would put me here. And the smallest it could be would be pi over 2. I'd take half of that, that would put me here. So half of any angle in quadrant 2 would be an angle in quadrant 1. And if I'm in quadrant 1, the cosine of that should be positive. So what I'm going to do here is say the positive square root of 1 plus negative 2 root 2 over 3 all over 2, which gives me the square root of 3 minus 2 root 2 over 3 over 2, which gives me the square root of 3 minus 2 root 2 over 6. And I'd say that's probably the best you can do with that, and leave the answer like that. But again, this is another thing we can use the half angle identity for. Okay, so here's another one. Verify this identity. Now, we can think of this identity, and it's, there's not an official triple angle identity, but we can think of this like it's a triple angle identity. It's the cosine of 3x, and we're basically trying to prove or verify this particular triple angle identity. Now, when it comes to doing these, we usually say start on the more complicated side and try and turn it into the simpler side. And that would be start on this side and try and turn this into that. However, for this particular problem, and for a lot of these, there's something that you need to know, which is we're going to do the other. We're going to start here and try and turn it into that for one reason and one reason only. Look at what's inside each of these trig functions on the right hand side. X. And on the left hand side we have 3x. It is much easier to take a 3x and bring it down to an x than it is to go the opposite way. I can take 3x and bring it down to an x as opposed to taking an x up to a 3x. It's very hard to make all these 3x's. That's the only way I'll be able to take this side here and turn it into that side there, is to somehow turn the things inside these trig functions into 3x's. But it's actually much simpler to take this 3x and bring it on down. And that's something you're going to have to understand. If I have a cosine of 4x or sine of 5x, it's much easier to take this and whittle it down to a bunch of terms with x's in it than it is to take a bunch of terms with x's in it and bring them up to a 4x. When we're just solving trigonometric equations, this is going to be something that's going to be pretty important. What you want is, anytime you verify these identities, you want the things inside the trig functions to all be the same. Let me erase some of this. We want all the things inside the trig functions to be the same. And if that's the case, I want all this to be the same. They're not right now. And I have the option, make these 3x's or make this an x. And I'm going to go make this an x. Alright, so just keep that in mind whenever you're doing anything with trigonometry. So if I'm going to write this as x, what I'm going to do is start breaking it apart. And again, the skill we learned in the beginning of the double angle identity is what we're going to use here. I'm going to write 3x as 2x plus x. That's still cosine of 3x. Now I have a sum. That sum can be written as cosine 2x times cosine x minus sine 2x sine x. Alright, now what do I have? I'm slowly, if you look at what's happening, the thing inside these functions is starting to get smaller and smaller. It's no longer 3x, now we have 2x and x. So now what I want to do is take these 2x's and bring them down to just an x. How? These are double angles, and we can use a double angle identity. For cosine, it's cosine squared x minus sine squared x. That's the double angle identity for cosine. That still has to be multiplied by cosine x. Minus the double angle identity for sine is 2 times the sine x cosine x, and that still has to be multiplied by the sine x. So if you look at what we got here, we distribute this in here and here. We're going to get cosine cubed x minus sine squared x cosine x minus 2, if these get multiplied together, sine squared x cosine x. These are both sine squared cosines. I have a minus 1 and I have a minus 2, so that gives me cosine cubed x minus 3 sine squared x cosine x, which is exactly what was on the other side of the equation, thus verifying the identity. And if you look at what we did, everything inside these functions is now down to an x. One more. Verify this identity. Okay? And this shouldn't be here. Okay? So what I'm going to do is I'm going to say, alright, well, let's start somewhere. I think this is a pretty easy one to recognize. That I'm going to start with this. These are half angles. So I'm going to use the half angle identities. And then we got squares. So we think about what the half angle identity for sine is, the half angle identity for cosine. So for sine, it's plus or minus the square root of 1 minus cosine x over 2. And then that has to be squared because of this. Then the half angle identity for cosine is plus or minus the square root of 1 plus cosine x over 2, and that has to be squared again because of that. Now if we're squaring this, if we square a plus or minus, it just becomes plus, and if we square a square root, it cancels, so I get 1 minus cosine x over 2 times 1 plus cosine x over 2. So if I'm multiplying these together, I I can multiply numerators and multiply denominators. So if I multiply the denominators, I get 4. If I multiply the numerators, I have to distribute all this out, and I'm going to get 1 minus cosine squared x. Because if you look at this, these are conjugates. And if they're conjugates, when you multiply conjugates, you should have the difference of 2 squares. Okay, we're still looking to get this as our answer. Well, we only have one more step. We know that sine squared plus cosine squared x equals 1. Or cosine squared x equals 1 minus sine squared, or sine squared equals 1 minus cosine squared. So this is sine squared. So I end up with sine squared x over 4, which is exactly where I wanted to go. So now you've seen a couple of ways we can use the double angle and half angle identities. You've seen other identities as well. So when we look at these verify the identity questions, which is really just getting you skills in simplifying trigonometric expressions, we can use the reciprocal, the quotient, the Pythagorean, the even-odd identities, the sum and difference identities, the cofunction identities, the double angle identities, and the half angle identities to do this. And you're going to have to learn when to use what, and sometimes it's obvious. X over 2 kind of tells me right away, half angle identities. Sometimes it's not. The skills and the tricks we've learned along the way should always be in the back of your head as to what you should do when. And sometimes the first thing you try doesn't work, like we've said before, but you want to keep trying until you can get one side to turn into the other.